Let's begin today with reviewing decimal and decimal place value. We left off with decimal multiplication, and we are going to spend a lot of time on the next class period about decimal division. But before we leave the decimal system, I want to go back one more time to the idea that all of place value is base 10. So the big deal in intermediate math about the decimal point and doing decimal math is getting control of that decimal point. And so understanding too that the decimal system is on base 10 even when we're behind the decimal point and the correlation to the negative exponent, which we showed you last week. But let's take a number and let's review the place value. Let's say we have 3,740 and 36 what? 10,000ths. That's the zero place exponent. This is 36 10,000ths. 4 zeros, 4 places behind the decimal point, and then the 6 is in this spot right here. 6 times 10 to the negative 4. There's all kinds of applications that are going to be coming relatively soon for your intermediate students with respect to base 10, with respect to the decimal point. Eventually, they have to be able to do scientific notation. Also, they will be doing a lot with the metric system. So the decimal place value is critical in teaching the metric system. It's critical in being able to multiply and divide by powers of 10, which is actually what's being done when you convert metric measures. So we need to make sure we've got the decimal point down. We need to make sure that we understand how to write this in expanded form, and we also need to understand how to convert numbers into scientific notation. In today's world, we have to work with very, very large numbers. Think chemistry. Also, very, very small numbers. Think microbiology. All right, so we need to be able to comfortably work in the decimal place value system. Decimal basic operations with decimals. Remember addition and subtraction. It's just an expansion of addition and subtraction of whole numbers. But decimal place value is the most important thing we need to emphasize concept-wise so that we can apply it right away and also down the road to the metric system and scientific notation. How would this number be written in expanded form using exponents? This is the thousands place. That corresponds to what power of 10? Thousands place is what power of 10? 10 to the third. Okay, so if we were going to write this in expanded form, it would be the 3 is equal to 3,000. Right? And so more and more as we start using the decimal point, start understanding the idea that the place value system is literally on base 10. It's not something that we memorize. Tenths, hundreds, thousands, 10,000s. We don't memorize place value in intermediate. We start understanding place value in intermediate. So the value of this 3 is 3,000 because it's in the thousands place. What is the value of the 7 in expanded form using an exponent? It's in the hundreds place. So its value is, this is exactly what we're talking about when we say that the place value system is on base 10. The value of each place is literally a power of 10. Then we have 4 is in the tens place. That's first power. There's nothing in the ones place, 10 to the 0 power. There's nothing in the tenths place, 10 to the negative 1. Nothing in the hundredths place, 10 to the negative 2. We do have another 3, and this is in the thousandths place. So the little th kind of translates into the negative exponent. What's the value of the 6? Here it is. It's in the 10,000ths place, 10 to the negative 4. That would be how you expand that number using exponents. So 7th graders in particular have to change their expanded form from writing the actual place to using, that's 3 over 1,000, 6 over 10,000. So there's expanded form and expanded form using exponents. Okay, so place value is going to become more and more important. This is, decimals are really started in grade 5. Fifth graders are not familiar with exponents, are they? Seventh graders have to start becoming familiar with exponents. Seventh graders also have to do scientific notation and even operations in scientific notation. So we have to have a thorough understanding of the decimal point so that we can start using it. So the first thing we're going to do is we're going to understand our place value. We also have to do a little bit of rounding with the decimal point. We talked about significant digits a little bit on Friday. Let me remind you, when you're rounding behind the decimal, sometimes you will have a significant zero. For example, let's say, well, it doesn't matter what the whole number is. Let's say I want this rounded to the nearest hundredth, which is right here. What happens to that 9? I can't round it up any further. The 6 requires a rounding up, does it not? So what do I have to do? To have this rounded to the hundredths place, I have to keep that 0. So this rounded to the hundredths place cannot be written 4.7 or 4 7/10. It must be written 4.70 because it has to indicate that it's been rounded to the nearest hundredth. So that's a significant 0. That's 4 70/100. One thing that you can teach your students to do, this is important, you can teach your students to read the number after they've rounded it. For some reason, I've told you in the past that rounding behind the decimal point causes confusion to 5th graders. Why should it? It's no different. You find the place that you're rounding to, the 9, you look at the digit before it, like to call it the next door neighbor, and then you round up. If it's 5 or more, you drop it if it's 4 or less. For some reason, they have a real trouble with it. Even the 7th graders, they don't round to the right place. So teach your students to read the number after they've rounded it. So this says hundredths, right? So when I read this, how should my answer end in? Hundredths, not tenths. This is incorrectly rounded. Read this, 4 70/100. What? Read this. It's incorrect. Okay? Even in front of the decimal point, if they take a second to look at what they just did and read it, they will get it correct. How do you get them to do this? You do it in class. When you ask somebody to round something, you don't let them say 4.7 or 4.70. That's even worse. That's not an O, is it? It's our lazy, slang-filled patterns of speech even come into play in math class. All right, so make them read things. So if I take this number and round it to the nearest, let me add some digits here. Let's add 1 here, let's add an 8 here, let's add a 4 here. Round this to the nearest tenth. Somebody? Round this to the nearest tenth. Anna, can you do that for me? 834.
And 60 or 700.
Tenths. Tenths. Okay. If the directions say round it to the nearest tenth, then it ought to read that way, right? Or if I want this rounded to the nearest tens, that one doesn't quite work because, I mean, it's 834 30, but this still is the tens place. But behind the decimal point, where you do have the most confusion and mistakes with rounding, make them read it out loud, make them look at it and say, does it match? Does this read tenths? Then it's rounded to the tenths. Okay. What is this rounded to the nearest? What is this rounded to the nearest hundredth? We've already done. Nearest thousandth. 834 and 996 thousandths, or 696 thousandths. So we've got to make sure that when we're rounding, our place value matches our directions. Okay? For some reason, like I said, there's always a big problem with rounding behind the decimal point. So we have to have means to overcome that. All right, back to place value and back to multiplying and dividing by powers of 10. What are we doing here? Every time we move places, what are we doing? We're multiplying by a 10. So let's take my original number. Let's take my original number and let's multiply it by 10 squared. That's the same as multiplying by 100, isn't it? But I am not going to do it like this and rewrite all those zeros and rewrite all those digits. When we multiply or divide by powers of 10, all we're doing is changing places. Okay, we're changing places by 2 digits. So this is going to get 2 digits bigger. So now thousandths becomes, or 10 thousandths becomes hundredths. All right, so when we multiply or divide by powers of 10, all we do is move the decimal point. And this is true, this is now going to be applied to the metric system. The metric system is base 10 as well. The metric system is deliberately base 10. And all we do with the metric system is move a digit each unit instead of moving a digit or moving a place each power of 10. When we change in the metric system, we are moving the decimal point. For example, if I have 4.8 kilometers and I want to convert that down to the base unit, I have hectometer, decameter, meter. Those two are not very useful. They're mostly placeholders. We don't need them for measurements. So what have I done? I've moved 3 units down, so I have to get 3 places bigger. So this is going to go 1, 2, 3. So 4,800 meters. So this moving of the decimal point is something that has to be established long before you get to the metric system. So part of being able to do decimal math is being able to multiply and divide by powers of 10 without actually doing the computation. All right, so what if I take my number and divide it by 10 squared, divide it by 100. There's no difference between these two, is there? Or actually, there's no difference between these 3 or these 4. They mean the same thing. Divide by 100 is the same as multiplying by 10 to the negative 2 power, which is the same as dividing by, multiplying by 1 over 10 squared, which is the same as multiplying by 1 over 100. It's all playing with the decimal point and place value names. All right, so this is the hundredths place because it literally is 1/100th. So when I divide, we're done with the multiplication. When I divide by a power of 10, it's the same as multiplying by a negative exponent, which is the same as multiplying by a fraction. I'm going to divide. So when I divide, my number gets smaller by 2 places. -2 versus +2. Biggest problem with the metric system is moving the decimal the wrong way, right? When you're converting metric units, the biggest problem is moving the decimal the wrong way. Well, why is the -2 exponent consistent with the number line? Think about your number line, your positive and negatives. Everything about mathematics is consistent. Numbers to the right of 0 are what? Positive. So when we multiply by a positive exponent, which direction do we go? To the right. The right is always positive. Left is always negative, is it not? There's never going to be any contradictions in how math is set up. So when I multiply by 10 to the -2, or I divide by 10 squared, that's the same operation. Which way is this telling me to move the decimal point? Which way? Left. Negative is always left. Positive is always right. All of these things in mathematics all work together. Okay? Even in 7th grade, when we start doing a little bit of number lines in the pre-algebra section, x is x is greater than 3. And I'll have 7th graders and even 9th graders ask me, which way do I shade? Okay? And keeping my face neutral, trying not to roll my eyes, right? I'm going to say, what do you mean, which way do you shade? The arrow points to the right. It's telling you which way to shade. There are no inconsistencies in mathematics. Which way do I shade? Okay, that's like saying, who's buried in Grant's tomb? Which way do I shade? To the right. Positive is always to the right. Larger is always to the right. Greater than points to the right. Less than points to the left. Division is to the left. Negative exponents move to the left. Okay? And that follows through with scientific notation. Mathematics is extremely consistent. It's the easiest subject to teach. Okay? So moving the decimal point is not a flip a coin, hope I go the right way. It's do what it tells me to do. Negative exponent means left. Just like negative numbers are to the left on the number line. Just like numbers that are less are to the left on a number line. Everything is consistent. So we've got to get that idea down. There's nothing random about mathematics. There's nothing hard about the metric system. What's hard about the metric system is it's unfamiliar. It's actually a much superior setup, much easier because it is base 10. It's based on place value. But if I haven't taught place value with my decimal system correct, I'm not going to be able to apply it to the metric system. And the metric system is going to be a big problem. You're going to have students constantly moving the decimal the wrong way. And it should become more and more obvious to them. Math is not random. Which way do I go? You go the way it tells you to go. Negative tells you to go to the left. Okay? So, what is this number then? Times 10 to the -2, which is the same as divided by 10 squared. I move that decimal 2 places to the left. We can add all these other digits because it tells me to go to the left. I'm not going to sit there and say, okay, I'm multiplying. No, I'm really dividing, so I got to get smaller, so I go to the left. No, the exponent's already told me which way to go. Just like this tells me on my number line that I am shading, going downhill, shading to the left on the number line. Okay? It's consistent. So you've got to get your decimal place value down. And here's an example where, yes, I am doing a lot of expansion in intermediate math. I'm adding tools to my toolbox in intermediate math, but concept is still the most important. What have we said over and over again about concept? Success is understanding. So success in doing decimal math involves understanding decimal place value. And then success in converting metrics and understanding the metric system comes back to understanding place value. Success in scientific notation and even success using significant digits comes from understanding the system. Okay, and that's not something that students do on their own. Some students do, most do not. So we've got to strive to reach their understanding of the decimal system, not just make it through the chapter on decimals. Okay? Not just get good grades on the homework in the decimal chapter. We want to try to get them to understand the decimal point. Okay? I've told some students before, and even their parents, made a statement like this: I don't care what grade you get in my math class. What do I mean by that? In the grand overall scheme of life, it doesn't matter your GPA on your transcripts, at least not very much. Maybe trying to get a job. But does it really matter what grade they got in 5th grade math? Does it? No. What matters is, did they develop math skills? Do they understand the math that a 5th grader and then a 6th grader needs to understand? You can teach to getting good grades. Do we criticize public education for teaching to the standardized tests? Yes. So we shouldn't do the same thing by teaching, skipping, actually doing the students' work for them. Right now I have several students struggling in 7th grade math. I can get their grades up tomorrow and next week by going through all the problems with them in detail so they don't have to think on their own, skipping some of the harder things. But does that help the students? No, it doesn't matter if you struggle in math and maybe you don't get a nice A or a nice B. What is important in math is that you understood the concepts, that you acquired math skills. So don't teach to your grade book, okay? Teach to the students' understanding of concept, teach to their ability to solve problems, teach to their ability to do procedure, not to get a good grade on their test, okay? So just like we'd be very critical of the teachers in the state of Indiana to teach to the I-STEP, standardized tests. Okay, we shouldn't be teaching to our grade book either. All right, so make sure that you do that and make sure that you strive to reach understanding, even though I've told you, all right, and the theme of our class is adding what? Tools to the toolbox. We can't ignore understanding, even though we will be doing a lot of procedure and teaching a lot of multi-step things. So keep that in mind so that when you're teaching, you have the proper perspective. Because sometimes you might be under a little pressure for your students to do better. Right? I'm not saying that you constantly teach over their heads and that's not accomplishing anything either. So make sure that you're striving to reach their understanding, especially with the decimal system. Okay? Many times I've thought later as a teacher when I'm teaching something in, especially in the 7th grade math, I see a new tool or I see a concept and I think to myself, why didn't somebody ever teach me that? I don't remember being shown that. I had trouble with percent math in 6th grade, still remember it. I couldn't figure out when to divide and when to multiply. And then once I got that conquered, I couldn't figure out which way to divide. And that's totally no reason for that. I just didn't understand what I was doing. So you want to strive to reach the student's understanding. Okay, so sermon over. Let's continue with our math content. Let's apply our decimal place value You need to be able to multiply and divide by powers of 10 and easily manipulate that decimal point so that you can do scientific notation, so that you can easily convert metric to metric units. So let's just practice scientific notation. Let's say I have a really, 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 really tiny number. Okay? If you've ever put a very tiny number or a very large number into your calculator, and then you hit the function key and it puts it into scientific notation, some students hate that because they can't get it out of scientific notation when they're using their calculator. So we need to be able to go into and out of scientific notation. Typically, to put a number in scientific notation, you're going to want your whole number parts, the part that actually has a number in it, to be at the one digit in the whole number, one whole number, and then typically one digit behind, sometimes 2 digits behind. So usually you would do it so that this is 3 7/10 in the actual numbers. Okay? Where is this decimal? It is actually, we moved it here, so the decimal is actually 1, 2, 3, 4, 5, 6, 7, 8 places. Where? To its left. So I have to use a negative exponent. Left is always negative, right is always positive. Okay, so that number in scientific notation is 3.7 times 10 to the negative 8. Okay, small number, negative exponent. Does that make sense? But you see the idea of left and right. It's not a mystery. It's not flip a coin. Which way do I move the decimal? Okay, it's not. So to write very small numbers, we use scientific notation so we can actually change the place value. And then we can do operations on this number, can't we? We put it in the same place value, we do the operation. We don't have to ever do a problem with all those zeros in it. That's what the calculator does. Okay? So can you put numbers in scientific notation? What if I had this number? What is that number in scientific notation? Remember, typical procedure is having 2 digits there. Because once you're that little, that 8 doesn't really do a whole lot for my number, does it? So typical procedure is 2 digits, one in front, one behind the decimal point. And again, the decimal was here, I moved it here. Where is the decimal really? The decimal is really 1, 2, 3, 4, 5, 6, 7 places to the left. That's where the decimal is really, so I use a negative 7. Do you get the idea of the left and right versus the negative and the positive exponents? Okay. So typical procedure in scientific notation is to actually round it there. Because that number is so small that 8 doesn't have a whole lot of meaning. What if I have a number like this? I'm going to put a bunch of digits in here. We use this all the time. This is billions, right? After a while, when we're talking 300 billion, does this number have any meaning? And do you think something is actually that precise that we need the 15? What about this number? We don't need any of these. What we would do here is we would round it to 3.2. Okay, how many places is the decimal really? The decimal is really, we moved it here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places to the right. That's a very large number. And you put it in your calculator, it's going to flip it to scientific notation. Okay? We do this all the time in story problems. All right, let's say the population of, I don't know. I don't know any exact numbers. Let's just make up numbers. Let's say the population of Mexico City is 3, it's bigger than that, but let's just put a number up. Here's a population number. Do you really think we can do population down to a single person? Or 10 people? 100 maybe. What do we just say? We just say, oh, there's about 3.2 million people in such and such city. Right? We do it all the time. What's the difference? What is million? 10 to the 6th. We move the decimal. The decimal, we moved it here. It belongs here. So it's actually 6 places to the right. So it's times 6. What's the difference? We do it all the time. Okay? We would say that we would never say when we're giving populations that the population of such and such a city is 3,175,645. We don't do it. It just simply can't be that precise. All right? So make sure that, yes, we know our decimal addition, we know our decimal subtraction. A lot of that is simply procedure. All right? Decimal multiplication involves more understanding. Like I showed you the last class period, it involves relating it to fractions and not forgetting the denominator. But more important than any of the actual operations, even in division, which we'll cover next time, we have to solidify their understanding of decimal place value. Then we can go to multiplying and dividing by powers of 10, which is done by 5th graders. Then we can proceed to metric unit conversion. Then we can proceed to scientific notation. Math is such a building process. Building math skills requires years of practice. It requires building on a solid foundation. So if we want to use our math in our science classes in the future, we have to understand decimal place value, right? The next thing I want to go over is actually in chapter 4 of your math book, and I want to go over your proportion skills. Another area of mathematics for intermediate level, which is not done in primary level and even in regular elementary level, is the idea of ratios, rates, and proportions. Ratios, rates, and proportions. What are these? How are they used? Ratios, rates, and proportions. Okay, and here we have to do a little bit of tethering. First, I'm going to introduce the terminology, right? Our teaching progression begins with terminology. There's really not any math facts with ratios, rates, and proportions. And then we have concept, procedure, and this is pretty much kind of a new thing. It's kind of a new thing for 6th graders. Not done really for 5th graders. 7th grade, they act like it's a new thing. Okay, so we have to make sure we start with terminology. This is a new concept, a new area. We've done our whole numbers, we've done our fractions, we've done our decimals. Now we have to cover ratios, rates, and proportions. What is a ratio? What do we do with ratios? A ratio is a comparison between two like quantities. Okay, so I'm going to compare. Both of these are comparisons, like quantities. Basically meaning we have the same unit. Rates are also a comparison, but rates involve, they're unlike quantities, they involve units. A typical rate, probably the most The most well-known rate is miles per hour. And then once you start getting your own car and buying your own gas, you start being concerned with miles per gallon. Okay, so this is a comparison between two unlike units. Miles per hour, feet per second, if you're doing a science computation in physical science or physics. If you are learning how to type for keyboarding, you're worried about words per minute, other things like that. Once you also have to start buying your own groceries, you're going to be worried about price per pound, cost per pound, and things like that. So those are rates. Basically, they're both comparisons. And we usually use per for a rate. We usually use to for a ratio. And with the ratio, they're like quantities, so we don't consider the unit. All right, we might compare the ratio of, I don't know, in a population, maybe we will compare the ratio of English speakers versus Spanish speakers. Okay, we don't have a unit involved there. It would simply be a numerical comparison only, and it is going to always be reduced. So terminology, the difference between a ratio versus a rate. We're still making a comparison. Ratio is simply a numerical comparison. So we will reduce it down to the smallest number, literally ratio, between the two. And so that's a numerical comparison because they're like quantities or like units. There is no unit, or the unit cancels out, the unit is not considered. It is a numerical comparison only. A rate then is entirely different. This is a comparison between two unlike units, and so we think of it as per. How much does it cost per ounce? With gasoline, the price per gallon. Or with speed, miles per hour, kilometers per hour, feet per second, meters per second. Those are all rates. That's a comparison that involves different units, and so the units are key because think about miles per hour. That's a speed. Think of, these are all literally rates in the way that we use the word rate in common English usage. So ratio is a numerical comparison only that we reduce to lowest terms, the smallest numerical comparison between two like quantities. We usually use the word to, symbols with a colon maybe, also can be symboled with a fraction. But we are making a specific comparison in a specific order. So if I want to compare in my 7th grade math class, if I want to compare the number of girls to the number of boys, I would, since it's a numerical comparison only, I have to keep it in the same order, boys to girls. In that class, there are 3 girls and 5 boys, so my ratio would be 5 to 3 in that order. So with a ratio, it is a numerical comparison only, but it has to be a consistent comparison. I can't flip around the numbers and actually write girls to boys when I meant boys to girls. So it is a numerical comparison only, and it is written in lowest terms, reminiscent of and tethered to fractions. Okay? If you recall, we can go back to the fact that I have 5 boys and 3 girls in 7th grade math. So I would compare 5 to 3. I would compare 5 to 3, or 5 to 3. Okay. In 7th grade math, we've also learned a new term that is driving them crazy, and that's reduced rational form. This is reduced rational form. And they have to learn that word rational in 7th grade and 8th grade so that when I really get using it in 9th grade Algebra 1, it's not a big deal. What does the word rational mean? Mathematically speaking, not logically speaking. It means it can be put in the form of a fraction. Okay? And reduced rational form does not use mixed numbers. Look at the word rational. What do you see inside the word rational? You see the word ratio, same root. So frequently with rates, we're going to use the units and we're going to say miles per hour, but not with ratios. Ratios will be put in reduced rational form. So that means, well, if you've trained your students very well, they're going to really want to turn that into 1 2/3. But that's not rational form. So there is a tether to fraction math, but really not as much as you might think. Okay? Reduced rational form. So ratios are a comparison of like quantities. The unit, there is no unit, or the unit is not important. The unit cancels out when you reduce it, and ratios are always expressed in reduced rational form, which is not the same as fraction. In fraction math, 5/3 is considered what? Improper. No such thing with ratios. So we don't have mixed numbers. We're making a comparison. We're not writing a fraction. It's called reduced rational form. A very important concept to teach to 7th graders, because in algebra, we don't use mixed numbers. We use rational numbers, don't we? And the answer to an equation is usually kept in reduced rational form. It is not converted to a mixed number, because algebra involves rational numbers, not necessarily fractions. Okay? So that is a ratio. It's a comparison of like quantities. The units are either not there or the units cancel. It is a numerical comparison only, and it's expressed in reduced rational form. So we do kind of want to make a break from our fraction math. There's 2 reasons we want to make a break from our fractional math. And that is, first of all, is this idea of reduced rational form. A ratio is not a fraction, it is a ratio. It is a comparison. Yes, we reduce it, but not because it's a fraction. That's the first reason. And I'll show you the second reason real quick here. When you solve a proportion, let's say I have 3 is to 5 as 9 is to 15. Look at this proportion. In one sense, I'm going to use a word here, I'm going to use the word divorce. In one sense, we want to divorce our ratios from fractions and our proportions from fraction math. Do you know what some of my 7th graders do to this proportion? They cross cancel. Are you allowed to do that? It looks like it looks very similar to this fraction multiplication problem, doesn't it? And they see this 3 and this 15 and it just drives them nuts. They've got to cross cancel. We don't cross cancel proportions, do we? We cross multiply, which is the means extremes product property. So I don't want to bring up the fraction math. I'll pay for it later. Okay, I will. So I don't want to do it. I want to kind of keep it separate. So maybe this is an example of untethering, because this idea of cross-canceling accidentally on a proportion problem happens a lot more than I want it to happen. So I want to do ratios, rates, and proportions in a different light. And actually I want to work with them and proceed with them into percent math. I want to get out of the fractions. So it's a good idea to have the decimals in between. And even though I do use the word reduced, I want to use reduced rational form. Okay? That's ratios. Comparisons. It is a strictly numerical comparison. The units are not there. The units cancel out. It's written in reduced rational form. And then also with your ratio, you have to have not only a reduced ratio, you have to have a consistent ratio. You can't change the order of the comparison. The order of the comparison must be consistent throughout when you're dealing with that ratio. Then a rate. A rate is when we compare two unlike quantities. For example, let's say, I remember taking high school typing, literally on a typewriter, not a keyboard, and I had to work at my words per minute. All right? And I had Mrs. Varner in high school for typing, and we were always worried about whamp, whatever, words per minute, and had to get a certain amount of words per minute in order to get a good grade on my timed writings. And you had to have so many words per minute before you made so many errors, okay? No backspace key on the typewriter. So, and actually the keyboarding type computers, the teacher can shut the backspace off. So, anyways, words per minute. So if I typed 150 words in 5 minutes, that's about my speed. We had to get to 50 to get a good grade, and I worked and worked and worked and worked and worked. And Mrs. Varner still gave me a B. So I'm not bitter. No. Okay. What's my words per minute? This is a rate. So what do I have? I have to divide it out. And actually, when I'm doing a rate, most of the time I'm dealing with what's called a unit rate. That's what I'm doing with rates. Whoops, unit rate. What is a unit rate? It's the number per 1 minute, or the number per 1 hour, or 1 second. Okay, so what is my words per minute? I want a unit rate. I want how many words in each minute. So I'm going to divide by 5 or reduce it. And what do I have? I have 30 words per minute. Right, Mrs. Varner never wrote words per minute. She wrote WPM. Just like we don't write miles per hour, we write MPH, right? This is a unit rate. How many words in 1 minute? There are other rates. If you look in the book, you can see 4.1 is the section on writing ratios. 4.2 is the section on writing rates. And they begin with this rate, 26 miles in 4 hours. That would be 26 miles per 4 hours. But that really has no use. And you can see they reduced it down to 13 miles in 2 hours. That's a rate. Not very commonly used. We need to proceed directly to objective B, writing unit rates. We have to divide it down until the denominator is 1, which doesn't always come out even, does it? So then we have to use a decimal or whatever the directions tell us to. Usually a decimal, can be a fraction, definitely a decimal if we're dealing with unit cost. So the most important thing about the section on rates is the idea of unit rates. We don't think of this as 13 miles in 2 hours. We think of it as 6.5 miles per hour, or 6.5, okay? Same thing. The fraction is a little more accurate because I wouldn't have to round, but the decimal here is just as accurate in the case of a simple problem like this. So rates are when we compare unlike quantities, and they are reduced, but most commonly and practically speaking, we don't do rates unless they're unit rates as far as story problems go. So what is a ratio? What is a rate? Both of them are comparisons. Both of them involve comparing in order, but with a rate, the order is usually implied and practical anyways. We would never switch them around. And with rates, we want to deal with the unit rate. How many miles in 1 hour? How many words in 1 minute? That's why it's unit. Remember, unit doesn't always mean feet, inches, yards, miles. It can also mean the number 1. The units period is synonymous with the ones period. So unit, in this case, does not equal measurement. It equals the number 1. Don't forget that. Then we have our proportions. Proportions, we're going to further apply our ratios and our rates. Proportions are very important for application, but we have to begin with terminology. What is a proportion? This is section 4.3 in our textbook, and it's simply the best way to put this is a proportion is 2 equal rates or 2 equal ratios. Okay, so it can be 2 equal ratios when we're just making numerical comparisons, or for application problems, many times it'll be 2 equal rates. And we can actually solve a story problem, do an application problem with 2 equal rates. So we begin our proportion with 2 equal ratios. We had this problem here. Let's see, 9/15, 3 is to 5 as 9 is to 15. These are not equivalent fractions, though looking at them, can't tell the difference. Can you? I can't. So there is a correlation between a proportion and 2 equivalent fractions, but we want to try to stay away from it. Okay, rates, or ratios here. This is a ratio, and it is read 3 is to 5 as 9 is to 15. Colons, not times. The 3 and the 15 are both referred to as extremes. You can kind of see they're on the end of my proportion when I write it in proportion form instead of in fraction form. Then the 2 middle numbers, the 9 and the 5, are called the means. And we have a math principle that applies to proportions, and that is called the means extremes product property. Maybe we'll call it the means extremes product principle, means extremes product property. A lot of times they use it as cross multiplication. Our textbook here refers to it as cross products. I don't like that because cross products means something else in upper mathematics. So we'll just call it cross multiplication, or it is the means extremes product property. That states that if I have a proportion, a true proportion, in a proportion, the product of the means, which is 5 times 9, must equal the product of the extremes, 3 times 15. And this is obvious one, 45. This is obvious from the standpoint of the means extremes product property. It's also obvious from the idea that those fractions are equivalent. So those ratios are equal. But let's keep calling them equal ratios. Okay, you could solve this by saying, oh, 3 times 3 is 9, 5 times 3 is also 15. So that does work because math is consistent across the board. But I want to center in on the cross multiplication rather than the equivalent fractions, even on easy ones. Okay, so when we are solving a proportion, one of the numbers will be missing. It doesn't matter which one. And to solve it, we can find the missing number. Many textbooks use n. I'm so used to algebra, I always default to x. But you'll see n frequently. Here is a proportion. Do not cross cancel, cross multiply. There's the product of the means is 80. The product of the extremes is 16 times n. All right, do fifth graders know 16 times n is the same as 16n? I have to start training them with that. And then we're going to solve for the 16 by dividing both sides by 16. So n has to be 5. This can be intuitively done by saying, okay, equal ratios have to be like equal fractions. So this was divided by 2. This then is also divided by 2. X is 5. There's nothing wrong with that procedure. Hopefully we won't have somebody coming up with the idea that they need to cross cancel. So don't cross cancel, cross multiply. You're going to be doing 4.3 and solving proportions and so forth. In this book, they do use the letter n quite a bit, and they also have you round to the nearest hundredth. I want you to express your remainder as a fraction, not as a decimal. On the homework, you don't have to change it. I think it's on the quiz that I said that. So, okay, so we will pick up with ratios and proportions, and then we are going to park on division next time.